In this video, you will learn about inverse and identity mappings. So what is an inverse mapping? Well, to describe an inverse mapping, we can say that it would put a figure right back where it started. In math notation, we can write this with T for translation or transformation, and then a little -1 above that. So the -1 just indicates that it's the inverse, kind of like inverse sine or cosine or tangent is the opposite of the initial transformation. So for example, if you had this picture here, this triangle, and you were to move it over here, that would be a translation. Okay, the inverse of that would be moving it back this way. So back to where it started, that would be an inverse transformation. So that's indicated with the T and the little -1 above that. So if you compose the translation with its inverse, okay, it takes you back to where you started. So if we call this shape P, okay, we compose right here, we compose a translation with its inverse. So we do the translation first, and then we do the inverse second. All right, that would translate or move back to where it started. So it would map P back to itself. Now an identity mapping, by definition, is a mapping that puts every point back on itself. So it does not change the location or shape of the original object. All right, so with a mapping and its inverse, if you compose them, so if you compose the inverse with the original transformation, it's going to be equal to the identity mapping, all right, because it puts every point back to where it started. And we saw that in the last slide, right, with that triangle. All right, when you did the translation and then did the inverse, it put it back to where it started, which was the identity. So we can say that when you compose or put together the translation or transformation of any sort with its inverse, we get back out the identity, which is the letter I. All right, so it takes you right back to where you started. And it doesn't matter the order. You could do T composed with the inverse in this way as well. You do the inverse first and then the transformation, or transformation first and then the inverse of that transformation. All right, so we have what's called a product of mappings, which is basically another name for a composition of mappings. And so we dealt with composition in the previous lesson, and we're going to go a little more in detail with that here. So for example, if you were to move this triangle over here, okay, that would be a translation. We call that T. And then if you move that triangle again over here, that would be another translation of the same amount. So when you're doing the same transformation, over and over again, we can represent that as a composition or a product of mappings. All right, so just like with algebra, right, if you had two different things put together, like if you had T times T, that would give you T squared. Same thing here. If you compose translation with another translation of the same value, the same amount, okay, we call that T squared. So it's very similar, except instead of a closed circle, like a dot, like a raised dot, it's going to be an open circle right here to indicate a composition of mappings. All right, so the notation is the same, right? We have T squared, indicates that we have two translations back to back. Now let's take a look at inverse mappings a little more in detail. So if you were told to find the inverse of the following translations, okay, how would you do this? Okay, so with this one, we have a translation, and we are mapping a point to x plus 3 times y plus 2. Well, to move it back where it started, you'd have to now subtract 3 from x and subtract 2 from y. So that would be the inverse of that translation. So the inverse of that translation is x minus 3 and then y minus 2. And then if you were to look at some other transformations, maybe a rotation, for example. Here we have a rotation with the center at O, and then the angle of rotation is 45 degrees. So we start here, if this is the center point O, and this is some point. If you rotate it 45 degrees, it takes you somewhere about here. Now the inverse of that, to get it back to where it started, you have to do a negative 45-degree rotation to get back over to here. All right, so the inverse of a rotation would be changing the sign. All right, so this would be a rotation with center at O, and then negative 45 as the angle of rotation. Now what about a dilation? Here we have the center at O, and then the scale factor is 2. All right, so that looks something like this. If you have a triangle, okay, then you're going to create another triangle that's twice as large with the center at O. So it's going to look, maybe the center point is over here, for example. All right, well, the inverse of that, to go back this other way, would mean that you need to take 1/2 of the original size. So this one, you basically just do the inverse, so the multiplicative inverse, because you had it times by 2 to get this new shape. So you have to divide by 2. So divide by 2, so you do 1/2 to get back the other way. So the dilation would be just basically finding the reciprocal to get you back to where you started. So here the center point is still at O, but the scale factor is now 1/2 instead of 2. So make sure you know how to do that with translations, rotations, or dilations. Make sure you can find the inverse mapping if needed. Now let's going back to the product of transformations. Let's take a look a little more in detail with those. Here we're dealing with translations specifically. And here we have a translation that maps a point of xy to another point of 2x comma y minus 3. All right, so if that's your translation, okay, if we want to find t squared, okay, what that means is we are doing this translation twice. All right, so once we have 2x times y minus 3, you have to now do it a second time. So basically, you can think of plug in a 2x in here for x, and then a y minus 3 in here for y. So what's happening is, you can write it out like this maybe. So you have 2x and then y minus 3. What would that be mapped to? All right, well, keeping that pattern going, okay, we have to take 2 times whatever is here. That's what the x means, 2 times this. So 2 times 2x would be 4x. And then this y minus 3 means we take whatever's here and subtract 3. So we do y minus 3, which is y minus 6. So that transformation would take you to the point of 4x comma y minus 6. Now what if you were given t to the third power? So t to the third power would be the same thing, same concept. So you take the 4x and y minus 6, and this would be found by plugging into this. So in 4x, this 4x here, you plug in place of x into this part. So we have 2 times 4x, which would give you 8x. And then the y minus 6 goes in here for y. We have y minus 6 minus 3, which gives you y minus 9. So your location of t3 would be 8x and then y minus 9. Now let's try the inverse of t. So t to the negative first power. So the inverse of t would have to do the opposite of multiplying by 2, which would be dividing by 2, or taking 1/2 of x. All right, and then for the inverse of subtracting 3, we have to add 3. So we have y plus 3 instead. And that's the inverse. That will undo this transformation over here. Now what if you had t to the negative second power? Okay, what would this be? Well, if we know t to the negative first power maps xy to this location, okay, the negative second power, what you do is you have to put in this 1/2 x in place of x, and then y plus 3 in place of y. So what does that look like? Well, let's put it over here. We have t to the negative first power will map xy to 1/2 x and then y plus 3. All right, so if you have t to the negative second power, what we're doing is we are plugging in, okay, for x and y, we're plugging in a 1/2 x and a y plus 3 in place of x and y. So in place of x here, we put in 1/2 x, So we have 1/2 times 1/2 x, which gives you 1/4 x. And then here in place of y, we put in y plus 3. So we have y plus 3, and then plus another 3 to get y plus 6. So t to the negative second power would be 1/4 x, comma, y plus 6. Let's try another example. Here we have t composed with its inverse. All right, now we've said that when you take a transformation and compose it with its inverse, we get right back to where we started. So if we started with this point of xy, when you compose with the inverse, we're going to get back to that same point of xy. So that would be just x comma y. Let's take a look at one more example on this slide. Here we have the inverse of t, and then the inverse of t. So bottom line, this works basically the same way as exponents does in algebra, where when you have a power to a power, you can multiply the exponents. So you have -1 times -1 to get t to the first power. So what is t to the first power, or just regular t? Well, it translates or moves xy over here to 2x, comma, y minus 3. So that's going to be your answer. It's going to be a mapping to 2x, comma, y minus 3. And that's your answer. So we've seen multiple examples of translations. Now let's try one last type of problem, and that is with rotations. So with rotations, let's say we had this rotation of r. That's a fancy r for rotation. A regular r is reflection. And this r maps all the points 90 degrees about point 0. So point 0, or point O, sorry, is the center. And we're rotating 90 degrees. So what we're trying to do is we're trying to give the image of C with this picture under the following rotations. So assuming that O is the center of the square, okay, we're going to be rotating point C with the following rotations. All right, so here we have r squared. So the question is, where would this mapping go to? So r to the first power would take you 90 degrees, which would be from C over to D. That's going to be a 90-degree rotation. Well, r squared means we have to go another 90 degrees, which takes you down here, okay, to point A. So that mapping would take you from point C over to point A. Now what about r to the third power? Well, r to the third power would be another 90-degree rotation, which takes you over here to point B. So r to the third power would be point B. Now what about the inverse of r? Well, the inverse rotation of a 90-degree rotation would be going the other way. So instead of going in the positive direction, we're now going in the negative direction. So this would be a negative 90 degrees, which would take you to point B. So the inverse of r takes you to point B. All right, so that takes you to here for a negative 90-degree rotation. And then if you had r to the negative second power, that would be another negative 90-degree rotation, which takes you over here to point A. Now what if you were composing r with its inverse? Well, r with its inverse, you can do this the long way by realizing that r inverse would have to come first. That's going to be a negative 90 degrees, takes you over here. And then r to the first power, just regular r, would rotate it back over here 90 degrees. So it takes you right back to where you started, which would be point C. And we know that to be true because any transformation with its inverse will give you back out the identity, meaning it's going to take you right back to where you started. And that, in this case, would be point C. Now what about r to the negative first power to the negative first power? Well, here, the simplest way to think of this would be you have a power to a power, so you multiply the exponents. So you have -1 times -1, which takes or gives you r to the first power. So that takes point C and rotates it 90 degrees over here. Okay, that's a regular 90-degree rotation. That's what r represents. And that would take you to point D. So your answer here would be point D. And that concludes our lesson for today. We will see you next time.